Hey guys, welcome back to General Chemistry. Today we're going to talk about something called percent yield. Again, percent yield is one of those applications of stoichiometry. So, same disclaimer as before. If you have not studied stoichiometry, if you've not worked and practiced with those problems, I would go ahead and turn this video off and get yourself proficient at doing stoichiometry before you try to add this percent yield concept on top of it. But let's move forward. Percent yield. So first we're going to talk about the concept of percent yield before we dive into anything. So percent yield is mathematically defined as the actual yield over the theoretical yield. Okay, so this is the formula. Percent yield is actual over theoretical. Well, that's all good and well, but we need to figure out what is actual and what is theoretical. So we need to know what those two terms are or mean or how we find them in order to plug them into this equation. So first, theoretical yield. Theoretical yield is the maximum amount of product that can be made in a chemical reaction. And theoretical is exactly what it sounds like. It is a theoretical amount. So theoretical means this would be the amount of product we could make if theoretically everything was perfect. Theoretically, every single reactant that we put into the mixture completely reacted. There's no side reactions. We didn't spill anything. Nothing got stuck to the beaker. So in a perfect world, if everything went exactly as planned, theoretically, how much could we be able to make? Reality is not perfect. So the theoretical yield is always going to be a mathematical calculation, right? Math is theory. So the theoretical yield is what we're going to use stoichiometry to determine. Okay, we're going to use stoichiometry. The actual yield is the actual amount of product that was made when the chemical reaction was performed. So if you were in a chemistry lab, you would walk over, you would do the chemical reaction, you would produce a product, you would weigh out that product, and you would say, this is how much I actually got by doing the experiment. In a virtual setting, the actual yield will always have to be given to you, right? So the actual yield will be the value that's given in the problem. When they actually did the experiment, here's what they got. So this will be given in the problem or your findings in a lab. Okay. So actual is going to be our reality. What actually happened when we did this experiment is not going to be perfect. So once we have those values, so we use stoichiometry to calculate the theoretical yield, we put our actual yield on top, then we multiply that by 100 and we get what's called a percent yield. The percent yield is the ratio between the actual and theoretical. And it's typically expressed in a percentage format. So the percent yield essentially is, well, how efficient was this process? Here's what I actually got. Here's what I should have been able to get. And how close are those two? Do they match up or are they vastly different from one another, right? So if you were working in an industry and your job was to make a certain product, a certain type of chemical. If you had a high percent yield, so in the 80s, 90s%, your boss would be happy. 90% of what we're putting into this, we're getting out. That's a really good yield. Now, if your percent yields were like 25%, your boss would be really mad, right? So we put in 100 grams of reactants and only 25 of those grams are actually being used to make our products. The other 75 would be going to waste or a side reaction or spilled or whatever. So a low percent yield means you're not doing a very efficient job of making what you're supposed to make. So percent yield is kind of like our efficiency in the lab. Are we doing a good job making what we're supposed to make? So let's dive into a problem. Let's see how this is applied. Okay. So our chemical reaction is nitrogen reacts with hydrogen to make ammonia, NH3. If 18 grams of NH3 is produced by mixing 6 grams of hydrogen in the presence of excess nitrogen, what is the percent yield? Okay. So we've got some numbers in here that we need to kind of find a home for. We need to decide what it is that they're going to be used for. Okay. So 18.2 grams of NH3. Well, the best thing to do here is to look at, well, what is NH3? Well, NH3 is a product, right? So when they did this, they were able to produce or get 18.2 grams. That is going to be their actual yield. Okay. As we stated before, remember actual yield will have to be given to you in the problem. So when they tell you how much of a product was produced, that's going to be your actual yield. Now we have this other number over here, 6 grams of hydrogen. Well, hydrogen is over here as a reactant. So that 6 grams of hydrogen is going to be used to determine the theoretical yield. So we're going to use, in a stoichiometry problem, to determine theoretical. Okay? So to do that, we're going to, just like I said, set up a stoichiometry problem. So we're going to have to go from grams of hydrogen to moles of hydrogen to moles of our product, which is NH3, to grams of our product. Okay, so that's the stoichiometry problem that we're going to have to do. Okay, so let's do that. So we're going to start our unit conversion problem with the information that's given. So 6 grams of H2. Grams of H2 on the bottom, moles of H2 on the top, and in 1 mole, we've got 2.016 grams. Multiply across the top, divide by the bottom. So 6 divided by 2.016 equals 2.97 grams of H2. All right, so next step is to go from, no, that is not the right unit, moles of H2. All right, so the next step is to go from moles of hydrogen to moles of our product, right? To do this, we have to look at our balanced chemical equation. So the coefficient 3 is stuck to hydrogen. Oops, wrong way. And the coefficient 2 is stuck to the NH3, the ammonia. So we need to make sure we get those into our equation. Multiply across the top, divide by the bottom. So 2.97 times 2. Divided by 3, and we get 1.98, and now we're in moles of NH3. And then to plug it into our percent yield problem, we need to go ahead and take that last step to grams. So we're going to have 1.98 moles of NH3. Moles of NH3 down here, grams of NH3 on the top, and now I got to figure out the molar mass of ammonia, so we're going to have hydrogen, 1.008 times 3, plus nitrogen, which is 14.007, and I get 17.03. Multiply across the top, divide by the bottom, so 1.98 times 17.03, and we get 33.7 grams of NH3. Okay, so that was our stoichiometry problem. That was the first step to get to the percent yield. Now we need to plug this into our percent yield equation. Okay, so percent yield is actual over theoretical times 100 to make it a percentage. So our actual yield was the number that was given to us in the problem, 18.2. Our theoretical is what we calculated using stoichiometry, 33.7. And then we're going to multiply that by 100 to make it a percentage. So the percent yield for this problem, 18.20 divided by 33.7 times 100, our percent yield is 54.0%. Okay. So if I was working in an industry and my job was to make ammonia and sell it, a percent yield of 54% would be terrible. So what that means is about 50% of what I am putting into my chemical equation, about 50% is getting wasted to side reactions, getting spilled, getting lost, and 50% is going to actually make me a profit. So that would be a terrible percent yield. We certainly would want more than half of what we're putting in to it to come out the other side. But that's a percent yield problem. That's how you would attack it. I hope you guys found this helpful.